Hey dudes, howdy. It's Professor Suresh, delighted to be back again for my 19th video in process of publication on YouTube today, 23rd of May 2020. This time, I'll give you a basic idea of autonomous vehicles, reality in life by 2025. Questionable. We, Earthlings, propose, but ultimately he or she, God, supernatural power, only decides. I take it for granted that most of you atheists will agree. Done. Let me proceed with the topic selected. Okay. Autonomous vehicle, also known as self-driving vehicle, is a vehicle that is capable of sensing its environment and moves safely with little or no human input. Again, Wikipedia definition. I love Wikipedia. Okay. As you are aware, driving by self on Indian roads is a real pain at the wrong place and induces a lot of mental agony besides physical exhaustion. If you are financially affluent, you may go for chauffeurs, but it would cost you a bomb. Moreover, you are dependent on chauffeurs who are not trustworthy. Autonomous vehicles will free one of all these hassles, and the procurement expenses of these vehicles are bound to go down south once they become a reality, and majority of the population adapts ADAPT. Many cars sold today are already capable of some level of automated operation, and prototype cars capable of driving autonomously have been and continue to be tested on public roads in Europe, Japan, and United States. These technologies have arrived rapidly on the market, and the future deployment is expected to accelerate. Autonomous driving promises many benefits: improved safety, reduced congestion, and lowers stress for car occupants, among others. All of you are aware of onboard diagnostics in contemporary vehicles. Historically, vehicles were driven by various animals like bulls, horses, donkeys, etc. Then we switched to powered vehicles called automobiles, which were purely mechanical ones, unlike the vehicles which we use now, which are multidisciplinary by nature, utilizing mechanical, electrical, electronics, instrumentation, communication technologies. As a matter of fact, even now we use the term horsepower, HP, for the rating of electric motors and engines, and the origin of is of course horses, which were used in coal mines for movement of coal in olden times. Many major car manufacturers and several technology firms have announced the commercial production of highly automated vehicles starting in 2017. Many observers expect there to be a wide range of such models on the market by 2030, and some of these may be self-driving. It is not clear at present, however, to what extent these vehicles will be capable of self-driving in all circumstances, that too in countries like India. Most crashes involve human error. If greater autonomous operation reduces or estimates these errors, then benefits for road safety may be substantial. However, most driving involves no crashes. That's wrong in India actually. The real safety test for autonomous cars will be how well they can replicate the crash-free performance of human drivers. While results from early prototypes are promising, new types of crashes may emerge as autonomous technologies become more common. For instance, crashes resulting from the car handling control back to the driver or from mixing autonomous and conventional vehicles. Especially in countries like ours, India, the automobile design is so bad that most of the automobiles have failed the crash test. This is the latest figure based on the test results. They change the technology, they change the design itself, like make it very cheap. For other country, they design it one way. For underdeveloped country or developing country, they design it other way. Brand will be the same, model number will be the same, but there is so much variation in what goes inside the thing. The move towards autonomous driving may involve different technological configurations. Some rely on greater connectivity between cars and between the cars and the infrastructure. These entail the development of common communication protocols, encrypted security standards, and investment in new types of infrastructure or upgrading those which currently exist. Others rely more on vehicle embarked sensor platforms and require little infrastructure investment. Both models require precise digital representations of the environment, including high definition maps. The first path involves gradually improving the automation in conventional vehicles so that human drivers can shift more of the dynamic driving task to these systems. The second path involves deploying vehicles without a human driver in limited context and then gradually expanding the range and conditions of their use. The first path is generally embraced by traditional car manufacturers and the second by new entrants. Incremental advances in automation in conventional vehicles are unlikely to fundamentally change vehicle market dynamics. It seems likely that individuals will buy and own such upgraded cars much as they do today. Automated driving will be available for certain situations, for instance, when driving on motorways, parking a car, or handling stop and go traffic in case of congestion. Because the human driver must resume active control when prompted to do so, such conditional automation raises particularly difficult issues of human machine interaction that are not being satisfactorily solved. Fully self driven cars, on the other hand, will not face the same issue of human machine coordination, although their use will likely be confined to contexts where the vehicle can confidently handle the full range of driving complexity. Such highly specific contexts include particular roads and low speed operations. Self driving cars have a much higher potential for disruption. They may be deployed in fleet wide systems that would fundamentally reshape individual travel and have an impact on industries such as public transport and taxis. Vehicle automation is part of a much larger revolution in automation and connectivity. The recent hallmarks of these revolutions, personal computers, mobile telephones, and the internet, have converged and are now blending with machines that sense and manipulate the physical environment. These machines include not just automated motor vehicles but also drones, personal care robots, 3D printers, surveillance devices, and many others. Vehicles will change with the growing automation, but so too will their roles in society and in ways that are hard to foresee. Liability remains an important barrier for the manufacturers and designers of autonomous vehicles. Expanding public insurance and facilitating greater private insurance could provide sufficient compensation to those injured by an automated vehicle while relieving some of the pressure on the TORT, civil liability tort system to provide such a remedy. Enhanced vehicle insurance requirements by manufacturers, especially if combined with greater flexibility in the administration of this insurance, could also provide a third party check on the safety of the automated system. As automation increases, liability could gradually shift from drivers to manufacturers and original equipment manufacturers, shortly OEMs. However, the allocation of liability among these parties remains challenging and adjudication methods have yet to be developed. Modern autonomous vehicles can sense a local environment, classify different types of objects that they detect, can interpret sensory information to identify appropriate navigation paths whilst obeying transportation rules. Considerable advancements have been made in giving an appropriate response to unanticipated circumstances where either a backlash can occur in the vehicular system or some medium in the external environment may not behave as predicted by internal prototypes, especially human beings. Even animals do behave properly on Indian roads, but not the human beings. To carry out successful automation navigation in such situations, combining a variety of technologies from different disciplines that span computer science, mechanical engineering, electronics engineering, electrical engineering, and control engineering, etc., is significant. As I told you, it is multidisciplinary now. The timeline of autonomous cars began in 1926 with the world's first radio controlled car, Lincoln Wonder. Significant advances in autonomous car technology have been made after the advent of the vision guided Mercedes Benz robotic van in 1980, since when the main focus has been on vision guided systems using LIDAR, radar, GPS, global positioning system, and computer vision. This developed into the autonomous technologies present in modern cars like adaptive cruise control, lane parking, steer assist, etc. A transportation accident is one of the major causes of death in the world. By 2020, this world could prevent 5 million human fatalities and 50 million serious injuries. This is 2020. Is it happening? This is by introduction of newer and innovative technologies and investments in road safety from regional to international levels. Two fundamental technological developments currently have the potential to substantially transform the automobile market. The growth in electric drive technology and the digitalization of vehicles call for new technologies and skills, while also opening up opportunities for new business models and providers. This may challenge and threaten the existing business models and fortunes of established manufacturers. The German Federal Highway Research Institute devised a similar taxonomy like Society of Automotive Engineers SAE that differentiates vehicles driven solely by the driver, manual driving, driver assisted, semi automated, highly automated, and fully automated. Simply using a lane departure warning system, for example, is not considered automation. Lane departure assistance systems go one step further and assume steering control. Autonomous driving on motorways is considered highly automated, while driver independent driving in the city, example robot taxis, is classified as fully automated. The automobile has fascinated people ever since its invention in 1886 by Carl Benz, founder of Mercedes-Benz in Mannheim, Germany. A car can embody what is technically feasible as well as what is socially desirable. The generations of automobiles over the years are evidence not only of the technical progress but also of aesthetics, society, and cultural changes as expressed in automotive design and the materials used. Cars can be viewed as a demonstration of human achievement over more than 100 years in the field of electronics, informatics, mechanical engineering, art, design, and many other disciplines. In its essence, the automobile, with its features and functions, its appeal in aesthetics, reflects how many of us imagine what a society is capable of producing with input from various sectors. However, the fascination of the automobile is the result of not only its visible qualities but also of the possibilities and opportunities it offers. Mobility, freedom, and independence, as well as social status, are all advantages that many drivers associate with their cars. I don't know whether this is true. I have heard that if you want to open an account in Swiss banks, what we call as numbered accounts, unless otherwise you go to the bank in a Mercedes Benz, the banker will not even talk to you. I don't know how far this is true. So it was more of a status symbol. Although the automobile gives people control and power over a machine and the feeling of freedom, movement, pride, and pleasure, the desire for autonomous vehicles is not something new. Autonomous vehicles are the logical endpoint of a development that began with a crank handle in the motor car patented by Carl Benz. My grandfather had such a car, you'll have to crank it manually. No electric this thing for starting. And this has led to driver assistance systems such as adaptive cruise control, forward collision warnings, lane departure warnings, and blind spot detection. The idea of a vehicle not needing a driver is no longer a fiction, as shown in movies, especially English movies, James Bond, 007 movies, Transformers, okay, etc. And the underlying technology is well on the way to changing the economy, society, and our everyday lives. Some manufacturers of autonomous vehicles have already emerged from the concept phase and passed through tests or take their place on the roads. Currently, they operate in controlled environments but will be found soon within normal traffic. For example, an Audi car drove itself from San Francisco to Las Vegas, and another driverless Audi reached a maximum speed of 149.1 miles per hour, that is equivalent to 240 kilometers per hour on a racetrack. NIO EVs, NIO. EV stands for electric vehicle, new sports car, NIO EP9 completed the circuit of the America's Formula One racetrack in Austin, Texas in a spectacular 2 hours 40 minutes 33, okay, not 2 hours, 2.40.33 minutes. Mercedes has presented its FD 1515, which provides an impression of the autonomous mobilities of the coming years with its futuristic design and many innovative features. For several years, Google has been testing its well-known vehicles in California and other US states. Tesla has equipped some of its cars with a software, cameras, and radar, enabling them to drive autonomously in certain traffic situations. Volvo plans to put the cars that can drive in autonomous mode on the beltway around Gothenburg, Sweden. Many other car manufacturers such as Ford, General Motors, BMW, Toyota, Kia, Nissan, and Volkswagen VW are working on prototypes of self-driving cars or have already tested them in road traffic. The chief technical officers, CTOs of many car manufacturers and technology companies agree that achieving the first 90% of autonomous driving is nothing special. It is the last 10% that is the most challenging, because the traffic situations are so dynamic, and especially in urban areas, that makes a difference. That is, achieving perfection is practical impossibility. Achieving absolute perfection, 100%. That's why the vehicles have to be tested in as many traffic situations as possible, so that experience is gained on the reactions. This is where simulation can come into play. Simulation is used for training race car drivers, for steering ships, for flying planes, etc. Even operating costly CNC machines. The same thing needs to be applied for testing of autonomous vehicles also. Toyota and Research and Development, RAND Corporation, have published calculations of the number of miles self-driving cars have to be tested before they can be assessed as roadworthy, because the algorithms required for driverless cars undergo self-learning in multiple road traffic situations. It has to learn like human beings, that's why we call it as self-learning. The more traffic situations these algorithms are exposed, they are better prepared they are to master a new situation. So the testing conditions should be more rigorous. Autonomous vehicles will only be accepted if they cause significantly fewer errors than the drivers, that is, higher reliability, safety, etc. Failure-proof design is a must for autonomous vehicles to become a reality. The world's first self-driving taxi has been in use in Singapore's University District since August 2016. It can be booked via a smartphone app to drive to selected destinations. Newtonomy, which operates this taxi service, named after Sir Isaac Newton, has already reported on enthusiastic passengers. Singapore transport authorities have also approved tests of 5 self-driving vehicles by Delphi Automotive Systems. The city state is regarded as an ideal testing ground for autonomous cars because the weather is always good, the infrastructure is excellent, and drivers there actually comply with the traffic regulations, unlike countries like ours. Rules that are not strictly enforced is as good as having no rules at all. That is how it is in countries like ours. Singapore also regards itself as a laboratory for testing new technologies and improving autonomous driving and the required infrastructure. Wanting to be at the forefront in the development of driverless cars, South Korea is building the world's biggest test arena near, it has built it now actually, Hwaseong K City, as it is called, is the size of a small town and lets researchers simulate many different traffic situations with narrow streets, lots of curves, traffic lights, roundabouts, parking spaces, bus lanes, a highway, and if requested, pedestrians and bicyclists crossing the streets. How about animals? That is left out. The 360,000 square meters, in square feet it is 3.875007 square feet test ground is one way in which South Korean government wants to help the country's automotive industry in its quest to launch self-driving cars. The artificial city will be open to South Korean car makers like Kia and Hyundai and to technology firms like Samsung, SK Telecom and Naver. Google demonstrated its first driverless car in 2010. A glance at the communications of many car manufacturers, suppliers, and technology companies shows that they usually refer to automated driving and only rarely to autonomous driving. The former term, that is automated driving, is the umbrella term that includes several phases of automation beginning with the driver assistance systems. The later, autonomous driving, describes the final stage of automation, the situation in which a system takes over all steering, accelerating and braking maneuvers. In this phase, a person is out of the loop and the car is able to act totally alone at all times and in all traffic situations. Vehicles that have reached this stage can be described as autonomous, driverless or self-driving. In short, the term automation is used to express the self-acting aspect of a machine. Autonomy goes beyond that, and beyond means that it's the self-governing ability of the entire system. In addition to cars, there are other vehicles that already move autonomously, particularly within the military. These vehicles can also be found in agriculture, self-driving tractors, even for cleaning the house. We have cleaning robots for that. Combined harvesters and other vehicles are used and communicate with each other to coordinate their movements. In general, in recent years, many driverless city vehicles and city buses have been put on the roads, especially in Europe and Asia. India is also in Asia. Most of them support the public transportation systems on defined roads. Another application is freight transport with autonomous trucks linking up into a platoon. At present, a truck with a driver takes a lead while the other trucks link up electronically. So the first truck is like the leader. At automated loading hubs, freight can be loaded from the one truck to another without any personnel involved, and the trucks can reform into new platoons. Autonomous guided vehicles, shortly AGV, and unmanned aerial vehicles, UAV, also known as drones, are a reality for material handling and movement. World's largest online retailer, Amazon, is already delivering packets to the customers using drones. Some hotels are using drones for delivery of food to the customers at the table. Unmanned space flights are also a reality. With full automation, there is no driver anymore. All the occupants of a vehicle are just passengers. It will take quite a few years until a lot of these vehicles are seen on the roads. but some vehicles are equipped with considerable automation already today. Level 0 is the starting point. There is no automation, and the driver steers, accelerates, and chooses to apply the brakes on the vehicle without any system support. With the levels 1 and 2, the system takes over more and more of these driving tasks. However, the driver is obliged to permanently monitor the system, the traffic, and the surroundings, and must be able to take over the driving function at any time. Level 3 means that the driver, level 1 and 2 is like driver assistance systems with cruise control, those kind of things. Level 3 means that the driver no longer has to continuously monitor the activity because the system indicates to him or her when it is necessary to take control of the vehicle. It's all sensor based. What is the sensor's malfunction? With the level 4, the system masters all driving functions in normal operation and in defined surroundings, but the driver can overrule the system's decisions. The last stage is level 5. The term automated vehicles refers to levels 1 to 4, while the terms autonomous, self-driving, or driverless vehicles refers to level 5, completely automated, 100%. The technologies upon which autonomous driving is based blur the boundaries between the automotive industry and the robotic, electronic, and software industries. Because we are using a lot of sensors, and the response time should be very short. It should be a few nanoseconds for corrective actions, otherwise there will be an accident. Software with the programming codes and algorithms, as well as cameras and sensors using radar, ultrasound, and lasers are all gaining importance. Meanwhile, the hardware of a vehicle, that is the chassis, suspension, and other mechanical parts, are losing importance. So it is not surprising that technology companies such as Apple, Google, Nvidia, Mobileye, Nutonomy, Qualcomm, and Microsoft are occupied with autonomous driving and have already actually developed their own driverless vehicles. Even the traditional automotive suppliers such as Aisin, Delphi, Bosch, Denso, Continental, TRW, Schaeffler, or Magna are either preparing their own prototypes of self-driving cars or working on key components for autonomous driving. The technology of autonomous driving will have a significant role to play in the success of electric mobility. As automation has a positive impact on energy efficiency, increasing vehicle automation will also significantly extend the range of electric vehicles. Pollution is also reduced. Noise pollution, air pollution. The essence of autonomous driving is the development of vehicles into cyber physical systems that comprise a combination of mechanical and electronic components. A vehicle's hardware and software exchange certain data about the infrastructure, the Internet of Things, shortly IoT, and the vehicle is controlled or monitored by a processing unit. In the future, each vehicle will communicate with the infrastructure, which is parking garages, parking spaces, traffic lights, traffic signs, and a traffic control center, which is called Vehicle-to-Vehicle Infrastructure Communication, or V2I shortly. Data on factors such as traffic flow, available parking spaces, and traffic light phases will allow the processing unit in the vehicle to select the best route and decide on a suitable speed. With vehicle-to-vehicle communication, shortly V2V, automobiles will be in contact with each other to exchange data. This will allow cars to coordinate their speed and maneuvers and to warn each other of dangers like rain, ice, fog, potholes, etc. Talking about potholes, even high roads in India are ridden with so many potholes. So many roads, highways, you cannot even go beyond 10 kilometers per hour. That is a condition of Indian roads. It is already clear that information and communications technology within a car is gaining importance and will lead to a paradigm shift in the automotive industry. Conventional car manufacturing is being transformed into an industry that creates digitized products requiring completely new skills. Car manufacturers will have to become more like technology companies in their culture, organization, and process, and must observe the spirit of this industry. It is no coincidence that the traditional American car plant sites in Michigan, Ohio, and Indiana are in difficulty, while a completely new mobility industry arises in Silicon Valley. All of you know Tesla Motors, right? Elon Musk, a crucial point for the further development of automated vehicles that they are able to master a diverse range of traffic situations. These cars are robots, so the software can only master those situations that were previously programmed or learned through machine learning algorithms. Therefore, autonomous driving is likely to be applied like artificial intelligence first, where traffic situations are straightforward and predictable. A typical case is a stop and go situation in congested traffic where cars alternate between standing and driving a few meters at very low speeds. Here, the traffic jam assistance that are already available can further be developed to cope with increasing speeds and more complex traffic situations. Here, we are controlling the traffic using real people, right? Traffic cops. Whereas in developed countries, the timing is fully automated. It senses the number of vehicles in a particular direction and changes the timing automatically. No necessity for human beings on the road. It's causing a lot of problems especially in Chennai and all as of now. Another example is driving on a highway where the complexity of the traffic situation is relatively low despite the prevailing high speeds. In urban traffic, there would have to be separate lanes for autonomous vehicles because of the diffuse traffic situations with the pedestrians, cyclists, and repeated changes of direction. It is to be expected, however, that starting with these scenarios, the software will be further developed so that increasingly complex situations in real traffic can be recognized and processed. Autonomous driving will not arrive overnight, and certainly not in other countries and regions at the same time. So it has to be done in phases, starting with the driver assistance systems that are already in use today, like parking assistance or traffic jam assistance. The processing unit will gradually be given more and more driving tasks. The speed of development mainly depends on progress within the software, including the recognition and identification of objects. It also depends on customers' willingness to use these systems and on regulatory and statutory conditions. Simulation is a very useful tool, as I said before, for development of software and required infrastructure for autonomous vehicles to be a reality on roads, not only India. Statistics and probability models with the real data would enable us to refine the technology further, make it perfect, to make it less risky, that is, enhance safety and comfort. Nothing is universally applicable. Customization, adaptation is a must. Never anticipate a smooth transition. Resistance will certainly be there, but it can be overcome once people get used to it. So it's a question of time. Getting the acceptance takes its own sweet time. Implementation of disruptive technology and paradigm shifts like these will yield in resistance. So some brainwashing is necessary, which will enable change in mindset of the general population. My objective was just to create an awareness, stimulation, curiosity of autonomous vehicles. Hence, let me stop here. Viewers who are more curious to probe further can browse the digital information readily available on net, besides research articles on this topic. Okay, we'll meet again real soon. Rest in peace and harmony. Always watch these videos with closed caption, subtitles for enhanced comprehension. I know pretty well that I rushed through to complete the presentation within 20 minutes max, but this time it's most likely that I exceeded the time limit. Bear with me. Bye.